Ions and ionic bonds, the epitome of thievery. We are talking about the theft of electrons here in order to create a zero overall charge. By the end of this video, you should be able to illustrate how an ionic bond is even formed using shell models. In the past, we learned that there are three types of bonding in chemistry. We've already talked about covalent bonding, and today we're going to be talking about ionic bonding. In the future, we're going to talk about metallic bonding really quickly, but ionic bonding is a little bit of a different animal. So we're going to spend some time talking about ionic bonds and how they're different from covalent bonds. If you check out the little graphic picture over there, you can already tell that ionic bonds are very much different than covalent bonds in the fact that they're less flammable than covalent bonds, they're harder and inflexible, so think like rocks or crystalline structures, they're soluble in water, and they have high melting and boiling points. We've also frequently referenced electronegativity differences, or the subtraction of electronegativity values, in order to determine whether something is polar covalent, nonpolar covalent, and now we'll learn what the range is for ionic bonds. So a range of 1.8 to 3.3 is our range for ionic bonds when we subtract two electronegativity values. Let's see if the bond between rubidium and chlorine is considered ionic. Well, if we find the value for rubidium, Rb here, 0.82, and we find the value for chlorine here, 3.2, we just have to subtract the two from each other. So 3.2 minus 0.82 gives us 2.38. 2.38 does happen to fall between the range of 1.8 and 3.3. So yes, a bond between Rb and Cl would be considered ionic. Let's see if you get it. Try figuring out the electronegativity difference between potassium and iodine. As a quick refresher, a nonpolar covalent bond's electronegativity difference range is 0 to 0.5. And a polar covalent bond's electronegativity difference range is typically 0.5 to 1.7. And as we just learned in the previous slide, an ionic bond's electronegativity difference range is 1.8 to 3.3. Go ahead and pause here and give it a try. Hopefully you found potassium, which is K, right there, 0.82, and iodine, which is I, 2.7. All we have to do now is subtract those two values. So 2.7 minus 0.82 gives us a final answer of, drumroll please, 1.88. Since that falls within our ionic bond range, we could say with confidence that this bond between K and I would be ionic. But what does it mean to have an ionic bond? Just hold on to your horses and you'll find out here in a quick tick. But before we can jump into that, we need to review some shell models in order to fully understand what an ionic bond is and why it occurs. Blast from the past, let's draw some shell models, one for sodium and one for chlorine. Sodium has 11 electrons and chlorine has 17. So let's put our little Na in the center for our nucleus, and we'll start with our first ring, which can only fit 2 electrons. And then our next ring, which can fit a max of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And we need one more ring to total 11. And there we go. There's the shell model for sodium. Some might say it's looking sodium fine. Now for chlorine. Chlorine has those 17 electrons. Let's put our Cl in the center for our nucleus. Same thing as before, we got to draw some rings, some shells. Fill the first with 2, the next with 8, and the next one can also fit 8, but we need to get to 17. And there you have it, the shell model for chlorine. Now what I'm asking you here is if we're only looking at the outermost electrons, the valence electrons, that's this guy up here and all of these on the chlorine. These are the valence electrons for each atom respectively. For sodium, would it be easier to lose that one electron or to gain essentially 7 others in order to be like a noble gas? Because remember, noble gases have their outer valence shell completely filled, and that's what makes them so stable. So for sodium, would it rather just lose the one, or would it rather go through the work of gaining 7 extras to be like a noble gas? Notice that if I just lose the 1, like that, I now have a filled outer shell, and sodium would behave like a noble gas in that case. It's got a full outer shell. Or it would need to go through the grueling work of finding 7 other electrons on top of that one just to fill the outermost shell. I hope you're catching my drift here. It's a lot easier for sodium just to exnay that extra outside electron, just lose 1, in order to essentially gain a filled outer shell. It's a lot easier to just lose that 1 to gain much more versus trying to gain 7 more. Oh, so much work. However, if we look at chlorine, chlorine has 7 electrons in the outer shell, and in order to be like a noble gas, it really only needs 1 more right there. It only needs to find 1 electron. So for chlorine, we're talking about either gaining 1 extra electron to be happy like the noble gases, or trying to find someone to pawn off all of these other electrons onto in order to have its full valence shell down below. So from chlorine's perspective, it's actually a lot easier to find 1 single electron and fulfill its noble gas destiny. Now, what's really convenient about the situation is that sodium needs to lose an electron to be happy, and chlorine needs to gain 1 to be happy. It's almost like they're soulmates. One is completely happy with losing and the other's happy with gaining. Or one's happy with taking while the other's happy with giving, so to speak. So what happens is that this sodium is going to be like, hey buddy, I'll just give you my electron. I'll pawn off my electron on you, therefore I can be happy. And chlorine, of course, will greedily take sodium's electron because it wants that electron like nobody's business. It also wants to be a noble gas. However, when this occurs, we need to keep in mind that electrons are intrinsically negative. They are literally negative charged themselves. So if you lose negativity, so sodium is literally getting rid of some negativity in its life, and when you lose negativity out of your life, you become more positive, right? If you're down, if you're gloomy, and you lose some of that gloominess, you become more positive, you become more optimistic. So in this case, sodium is down on his luck, and he's just going to lose that electron and become more positive. Likewise, when we're looking at chlorine, chlorine is taking on sodium's depression, so to speak, and taking its electron from it. But it wants to take the electron, don't get me wrong. It's happy to be in a more depressed state because now it's more like a noble gas when it takes on that extra electron. So now that chlorine has taken on extra negativity, it becomes a negative charge overall. As we've learned in the past, anytime that there are opposite charges near each other, like in polarity, they end up attracting to each other. So now sodium and chlorine have a bond, and this bond is what we call an ionic bond. The attraction between this negatively charged and positively charged atom. Aww, opposites really do attract. So just to reiterate here, sodium loses an electron. It loses negativity, which makes it become positive. While chlorine gains an electron, it gains negativity, therefore making it negatively charged overall. And just like my husband and I, opposites attract. So those positives and negatives have nothing better to do than to hook up. So sodium and chlorine are now hooked up, and they are a mate for life as your yummy table salt on your French fries. Let's see what would happen between beryllium and nitrogen by drawing the shell models first and determining which of these 2 atoms would rather gain or lose electrons. Go ahead and pause the video here and give it a try yourself before I give you the answer. Well, beryllium has 4 electrons, so let's draw that shell model. It has 2 in the first shell and 2 in the next shell. While nitrogen has 7 electrons. 2 in that first shell and a max of 8 in the next shell. So I will pose the same question as I did before. Is it easier for beryllium to gain an extra 6 electrons in the outermost shell in order to be like a noble gas? Or is it easier to just lose these 2 electrons and have a full shell down below? Hopefully you can see that it would be a lot easier for beryllium just to lose the 2 than to gain 6 extras. So beryllium is the one that wants to lose electrons. And when it does so, it would have to lose 2. For nitrogen, we need to consider how many it would need to lose or gain. Nitrogen would need to lose 1, 2, 3, 4, 5 electrons in the outer shell, or it could just gain 1, 2, 3 to be like a noble gas. I think it'd be easier to gain 3 than to try and lose 5. So nitrogen in this case is going to be the one that gains electrons or wants to gain electrons. And in this case, it wants to gain 3. Hopefully you're catching the drift here that ionic bonds are all about give and take. One of the atoms is going to end up giving and the other is always going to end up taking, just like a lot of relationships I know. So when beryllium loses 2 electrons, it now becomes positively charged, but not just positive 1, it lost 2. So it becomes positively 2 charged. When nitrogen ends up gaining 3 electrons, it's going to end up with not just a negative charge from the electron gain, but a negative 3 charge from the electron gain. By the way, this is also how we get our shortcut for the periodic table charges. For the first column here, they all want to become +1 charge. In this column, they all want to become +2 charge. Hey, that fits with the beryllium we just showed. In this column, they all want to become +3. In this column, plus or minus 4. This is just a reminder from the periodic table lesson. In this column, they want to become -3. Hey, we just saw that with the nitrogen. In this column, they want to become -2. And in this column, they all want to become -1. Of course, in the noble gases, they have 0 charge, and that's what everybody wants to be. So the idea here is that the loss or gain of electrons is what causes ions to form. In nature, atoms are typically neutral. They want to be neutral normally. So when atoms lose or gain electrons from that valence shell, they are no longer neutral. They have a charge on them, whether that's positive or negative, with a certain value. And when they get this charge, that is when we call them ionic, or that is when they turn into, quote, ions. That is what an ion is. And again, it all boils down to where the electrons are and what they're doing. So keep an eye on those electrons. Now we have a different word for each type of ion. If it happens to be a positive ion, i.e. a atom that has a positive charge on it, we call it a cation. And an easy way to remember that is that cats have cute little paws. And so you can think that cations are positive. They got cute little paws. They're positive. And anions are negative. So any of those atoms that end up with a negative charge with whatever value it might have, those are anions. I don't really have a cute mnemonic for that one. I think of anions kind of sounding like an onion, and onions make me cry when I cut them, so that's kind of a negative thing. I don't know if that helps you or not, but that's how I remembered it when I was in high school. Anions are negative. You must be missing an electron because I've got my eye on you. Anions also tend to be the atoms that are larger because they're the more electronegative atom. They're comfortable with taking on more electrons, more negativity. In fact, they want it. They thrive in that condition. So they're the ones that have the larger atomic radius, the bigger electron cloud that can host more electrons therein. So now that we know that ionic bonds are essentially just this attraction between a cation, the positively charged atom, and an anion, the negatively charged onion, ? Ionic bonds have that complete transfer of valence electrons, or theft. They steal or they give from the valence shell. And they always occur between a metal and a nonmetal. So if you go back to your periodic table and you happen to notice that there's a metal atom connected to a nonmetal atom, it's going to be an ionic bond. Whereas with covalent bonds, it was always and only and forever between only nonmetal atoms. So ionic bonds, metal and nonmetal together forever. The other thing to keep in mind here is that an ionic bond occurs in order to neutralize the charge. Effectively, when you put the +1 and the -1 together, they cancel out to make 0. So the overall molecular charge is always going to balance out to 0. Each atom will end up with that full valence shell from the theft or the giving or the taking and whatever. But overall, once they're together, the charge has to be zero. And remember, the whole reason they do that is to just be like the noble gases. I said it once, I say it again. Everything in chemistry has to do with the interactions of electrons. So they are very different in terms of the properties that they have, but they are caused by the same thing. What are the electrons doing? Where are they? And how are the atoms with the electrons interacting with each other? So because ionic bonds are due to theft or a full transfer of electrons, whereas covalent bonds are due to sharing electrons, there's kind of this gray area between them. So we can end up with a continuum of ionic and covalent bond and somewhere in between. So sometimes it gets a little fuzzy. Those electronegativity differences we talked about earlier, they're a good framework for deciding whether or not something is ionic or covalent, but sometimes there's this hairy region between the two. So keep in mind that the line in the sand here is always that covalent bonds are only nonmetals bonded together, and ionic bonds are only metal and nonmetal atoms bonded together. So in summary, what are ionic bonds? They are the attraction between a cation, a positively charged atom, and an anion, a negatively charged atom, via the full electron theft, or taking, or giving. The resulting charges, the positive and negative, causes the two atoms to attract to each other. And it's always going to be an attraction between a metal and a non-metal atom, and the overall charge that they have together balances to zero. And when it balances to zero, this means that together they are neutral, and they each have their own full valence shell. In other words, they complete each other. In the next video, we'll be talking about how cation and anion charges can be balanced in order to result in that overall zero neutral molecule. If you found this helpful, please like the video, and for more educational content, and to reach out to others that might find this helpful as well, please subscribe to my channel. See you next time.
No ducks, no glory.